I welcome everyone to this Power Electronics lecture series. So, in the previous video lectures, uh, we discussed with the importance of power electronics, motivation behind the power electronics, and then we started deriving a chopper. So, what is the issue with the chopper? So, based on that, we come up with the design called as a buck converter. So then we derived the output voltage for the buck converter as V naught equal to D into VDC. So with the principle of average voltage across inductor over a one time period is equal to zero. So based on this principle, the voltage across inductor, the average voltage across inductor over a one cycle is equal to zero. Based on this principle, we come up with the relation between output voltage and input voltage as a function of the duty. So the same principle I said it is applicable for the any type of converters. And again, there is one more principle we discussed in the first video lecture, the average current through the capacitor. The average current through the capacitor over a one cycle is equal to zero. So based on this relation also, we come up with the average current through the inductor is equal to output current for the buck converter. So this can be applicable for the any type of converter. So there are two important principles we have seen. The average voltage across inductor over a one cycle is equal to zero, and the average current through a capacitor over a one cycle is equal to zero. So based on these two principles only, we started deriving the converter analysis, and we come up with the output voltage as a function of duty cycle and the input voltage for the buck converter. Again, we saw the model waveforms, voltage and current waveforms for the different elements present in the converter. So after that, we have seen about discontinuous mode of analysis for the buck converter. So the same analysis can be carried out for the remaining converters also. So then we understood that if you can able to see the buck converter in the reverse direction, so then we come up with a boost converter, so where you can check the output voltage is going to be greater than input voltage. So here also in the boost converter also we followed with the same procedure. So the first we followed a KVL in the mode 1 and mode 2. So in the mode 1, when the inductor is in charging state, so we wrote a KVL equation and we found the voltage across inductor in the mode 1 during charging state. Similarly, in the mode 2, where inductor is in discharging state when the switch is turned off. So again, we applied KVL equation and found the voltage across inductor during discharging state. After that, we followed the principle of average voltage across inductor over a one cycle is equal to zero. So based on this, we come up with the output voltage as VDC by 1 minus T. So as you can see, the gain, the relation is going to provide greater than 1. The gain is going to be greater than 1 always. So this type of converter, we are naming it as boost converter. So and again, we applied average current through capacitor is 0. So over a one cycle. So based on that relation, we come up with the average inductor current as I naught by 1 minus T. So that is what we have seen in the previous video lectures, a detailed discussion about buck converter analysis, boost converter analysis. So with the principle of average voltage across inductor 0 over one cycle, similarly average current through capacitor over one cycle equal to 0. And we derived some problems also. You can go through the previous video lectures. So start with the first lecture and follow continuously. So in middle, if you join, you may not be understanding. So I request everyone to start with the first video lecture and keep on tracking the remaining video lectures. So if you're having any doubt, you can join in the group mentioned here. So you can ask the doubts directly. So come to the remaining part. Okay, before that, I said about bidirectional action of the converter. So I already explained that a buck converter and boost converter circuit wise, they are not different, both are same. So here, if I want to operate a buck converter, if you check this picture, so circuit, so if I want to operate buck converter, I'm going to trigger S1. So S1 is going to act as a prime switch, and the S2 I'm not going to trigger. So the anti-parallel diode of S2 is going to act. So the power is going to transfer from the battery. Suppose if I take an example where the buck converter input is battery, and oh, sorry, yeah, fine. The buck converter input is battery, and here it is a output. So then you can have the power transfer from the from this input to output, and it is doing a buck action. So let us have a real time example. So if I take the example where here it is a grid. So where here it is a microgrid. So DC link of the grid, grid voltage having a VG here. So here, if I take it as a battery, so here it should be battery. So usually, if we want to charge the battery, so the battery voltage is going to be typically less than the grid voltage. So where we need a buck converter. So what this buck converter do means it transfers the power from the grid to battery with the voltage matching of the battery. So it transfers the power from the grid to battery while the stepping down the voltage from the grid to battery. So now if I have the power flow from the grid to battery, I can write the battery voltage as D into VG. D into VG. So this is what the typical real-time application of these bidirectional converter. Suppose again, if I want to feed the power supply back to the grid from the battery, suppose the charging is done, so now there is a demand of the power supply, and it should be transferred to the grid, so now from the battery the power should be supplied to the grid. So we cannot directly supply power from the battery to the grid with a direct connection. There must be interfacing converter, so that this converter, it should be acting as a boost mode by operating S2 as a main switch, prime switch. So if you can see from the right to left, so I can have the boost converter here. So if I operate S2 as a prime switch, I'm going to trigger S2, and whereas S1 I am not going to trigger. So you can have a boost operation, and the power is going to be transferred from the battery to the grid, So this is how the bidirectional converter operates. So if you want to have power transfer from the battery to grid, so power transfer can be done while operating the converter in the boost mode. So again, if you want to have power transfer from the grid to battery, yes, power transfer can be done. It can be done from the left to right while doing the buck action, operating the S1 as a prime switch. So kindly change here. Here it should be grid voltage. Here it should be a battery voltage. So this bidirectional converter is going to help us to have both the power transfer according to the uh, power requirement, and while matching the voltage of the grid and battery. Okay, fine. So in the previous session, we have seen the average inductor current by applying a average current through a capacitor over a cycle is equal to zero. Average current through a capacitor over a cycle equal to zero. So when the switch is turned on, so the capacitor is supplying to the load with a current of minus I naught. So during a turn on state, D into T, during turn on state, that is D into T. When the switch is turned off, so the capacitor current becomes IL minus I naught, and this is going to happening in the T off. That is, I can write it as 1 minus D. So now if I simplify this, I am getting this one, IL average equal to I naught by 1 minus D. Again, I said, since the converter analysis I did without any consideration of parasitics, so definitely the input power should be equal to output power. We'll see this. So VDC input power, I can write it as VDC into IL. So if I take VDC here, so IL I can write it as IL average, I can write it as I naught by 1 minus D. So again, VDC I can write it as V naught into 1 minus D. So 1 minus D get cancelled. So the input power becomes equal to output power. So this is the relation I explained in the previous video lecture. So similarly, you can do for the buck converter also. So buck converter, what we understood. So again, we applied average current to capacitor over a cycle equal to 0. So from that, we understood that the average inductor current equal to output current. So again here, let us try to find the input power here. So input power is VDC into I switch average. Basically, the switch current, average of switch current is equal to input current because they are connected in series. So how to find the input current, I switch average current. So now you can just analyze the operation of the buck converter. When the switch is closed, the current flowing through the switch is equal to inductor current. So if I take a negligible ripple in the inductor, I can approximate the inductor current is equal to output current. So the switch average, I can write it as I naught. So this is seen in the switch turn on state. So in the mode 1. So that's why I can write it as I naught into dt plus, and when the switch is turned off, when the switch is turned off, obviously the current flowing through the switch becomes 0. So whole divided by T. So anyways, TT get cancelled. So the switch average current, and that is input average current, that is equal to I naught into D. So the input current for the buck converter, I can write it as the I naught into D. I naught into D. So again, when I substitute this input current in this input power, so you can check here VDC into input current, I can write it as I naught into D. So you know VDC into D is going to be V naught. So V naught into I naught, I can make it as output power. So in the buck converter also, in the ideal state, the input power is equal to the output power. So this is what the analysis we discussed in the previous video lectures. So please go through this. We had a detailed discussion about this buck converter and boost converter analysis along with the model waveforms also. So you can find the switch average current, switch RMS current. Similarly, the diode average current, diode RMS current. Actually, these are required to analyze the power losses in the converter. So once we have waveforms, you can find the RMS currents, average currents. So that is what with respect to buck converter and boost converter. So in the previous video lecture, I given an assignment for you. So design a buck boost converter. So solve the buck boost converter and design the L and C values. L and C values. So I asked you to do the analysis. Okay, fine. So in this video lecture, we'll continue with the buck boost converter design. So this is the circuit for the buck boost converter. You can check here. This is the inductor position. Previously, in case of buck converter, so the inductor is located at the output side. Whereas in case of boost converter, the inductor is located at the input side. So now if you see the buck boost converter, here it is located. Here it is located. So now when I turn on the switch, any converter, so you need to go with a two modes of analysis. One is while inductor is in charging state, let me take it as mode 1. Similarly, the second mode is going to be inductor is in discharging state. So based on this rule only, we are going to come with the output voltage as a function of input voltage and the duty cycle. So first you turn on the switch and inductor is in charging state in this particular mode. When I turn on the switch, inductor is in charging state. So try to analyze the voltage across inductor. So it is in charging state, try to analyze voltage across inductor. So let us take it as mode 1. Similarly, now when I turn off the switch, so previously the inductor is in charging state, so it tries to maintain the current in the same direction. So however, when I turn off the switch, so it has to track a path, closed path, to maintain the discharging current. So for the discharging current, it has to be creating a path, right? It has to flow in a path, so closed loop. So for that reason, so the diode should be connected in this particular direction so that it creates a path. So the current flows in this path. So that's why the diode should be connected in this manner. So anode to the output here, and the cathode terminal is connected to the one end of the inductor. So this is how the diode connection is going to be present in the buck boost converter. So now again you apply a KVL in the mode 2 and try to get the VL2. So VL1 during mode 1, that is VL on. When the switch is turned on, so what is the voltage across inductor? VL2 during mode 2, that is when the switch is turned off. What is the voltage across inductor? So apply average voltage across inductor over a cycle equal to 0, that is VL on into dt, or else t I can cancel it, because when I write a denominator t, so the numerator t get cancelled, so no, I am not going to mention the t here. So VL on into d plus VL off into 1 minus d equal to 0. So try to apply KVL and try to find VL on. Apply KVL and try to find VL off during mode 2. So mode 1 you apply KVL, try to find VL on. Mode 2 you apply KVL, try to find the VL off. Then you can get the relation between output voltage and input voltage. So you can check this here. So during mode 1, so I can write VL equal to VDC. So VL equal to VDC, or here VS. So similarly during mode 2, so this is the path, apply KVL here. So I can apply KVL as minus VL and then minus V naught equal to 0. So from this I can write VL equal to minus V naught. You can check here. So when the switch is turned on, the inductor current is flowing in this direction. So during this particular mode, so the diode is going to be in the reverse direction. Reverse, it is in blocking mode. It is in reverse biasing. So the current flows only in this path. So this is going to be in off state. So current won't flow in this path. Okay. So current only flows in this particular path. Okay. So this diode is going to be in the reverse biasing condition. So we'll try to see what is the voltage across this diode. Okay. So anyways, so whatever the charge stored in the capacitor, so this can be discharging state, in the discharging state and giving to the load and maintaining the output voltage V naught. So if I want to write a capacitor current, so since it is in discharging state, I can write IC equal to minus I naught. So this is what we have seen in the boost converter also, right? So when the switch is turned on, inductor is in charging state, the capacitor is in discharging state, and it is giving to the load. So since it is in discharging state, I asked you to put a negative polarity, IC equal to minus I naught. Okay, fine. So now come to the voltage, inductor voltage. So inductor voltage, when I turn on the switch, so the voltage across inductor I can write it as supply voltage. When I turn off the switch, again, don't change the polarity for the inductor. So take the reference polarity, plus here, minus here. So now if I apply KVL, minus VL, minus V naught. So here the current is flowing from the bottom to top. From the bottom to top. Current is flowing from the bottom to top. So always the current flows from higher potential to lower potential, you know, right? So then if I apply KVL, I can write the equation as minus VL minus V naught equal to 0. From this I can write VL equal to minus V naught. So you are having two equations. One is the voltage across inductor when the switch is turned on, that is in charging state. The second one is voltage across inductor when the switch is turned off, that is discharging state. So now you apply the principle, average inductor voltage over one switching period is 0. So what is the voltage across inductor when the mode 1 state, when the inductor is in charging state? So VL is Vs into D. So no need to put T here. So because the denominator T get cancelled. Okay. So Vs into D plus, what is the voltage across inductor during mode 2? Minus V naught. Minus V naught into 1 minus D. So equal to 0. So now I can write here. So VSD minus V naught into 1 minus T equal to 0. So from this I can get V naught output voltage of the buck boost converter as V naught equal to Vs into D by 1 minus T. So V naught output voltage is equal to Vs into D by 1 minus D. So here positive voltage I am getting. So why I am getting positive voltage here? Because I considered the polarity plus down minus up. So usually in the textbooks, so they keep the positive polarity in the upper position. So if I consider the positive polarity here, so definitely I'm going to get output voltage negative. So you can write output voltage negative if I consider so the positive here. Okay, so this is the analysis of the buck boost converter. So again, you can draw the model waveforms. So I already told you first while drawing the model waveforms, first draw the gate pulse. So the second one, see the inductor current. So when the switch is turned on, inductor is in charging state. Okay. When the switch is turned on, inductor is in charging state. Okay. So now what about the inductor voltage? So we had derived with KVL, right? So VL equal to VS, that is equal to VDC. So here I made a notation of VDC. So VL equal to VDC during turn on state for a time of T on. So this is T on, D into T. Okay. So dt, you know, right? T on by T. So during this turn on state, so the voltage across inductor is VDC. VDC and inductor is in charging state with the application of gate pulse to the switch. Okay. So now when the switch is turned off, okay, first we'll complete when the switch is turned on, the remaining voltage and current response for the switch and the diode. So when the switch is turned on, the voltage across the switch is ideally it is zero. And what about the current through the switch? The current through the switch follows the inductor current. So the same rising current shape, you can have it for the switch current. Okay. So now what is the voltage across the diode? So as I mentioned, the diode is going to be in reverse biasing mode. So let us prove why the diode is in reverse biasing. So for that, you apply KVL here in this particular loop. So when you apply KVL in the particular loop, so now let me take here it is anode, here it is cathode. Okay, so here positive we consider, right, reference, here it is negative. So now if I apply KVL in this particular loop, I can write it as minus VL minus V naught minus VAK equal to 0. So from this, what is the voltage appearing across anode to cathode? Means minus of VDC plus V naught. So minus of VDC plus V naught. See, this V naught comes across the capacitor also. So the voltage across the capacitor can be taken it as V naught itself. So minus of VDC plus V naught is coming across the diode. So since the negative voltage is appeared across the diode, so I can justify that the diode is in reverse biasing mode. So the diode won't conduct. So it is in reverse bias mode. As it is not conducting, the current through the diode is 0. And what about the current through the capacitor? So current through the capacitor is going to be I naught. As it is discharging to the load, I can take it as minus I naught. So here you can put it as this value, you can have it as I naught, and it should be in the negative as it is in the discharging condition. So this is what we can see when the switch is in on state, that is mode 1. Now when the switch is turned off, what is going to happen? When the switch is turned off, inductor is in discharging condition. Okay, so the current is going to be in the falling slope. Okay, so current is going to be in the falling slope. Now again the voltage across inductor is going to be VL equal to minus V naught. So just apply the KVL. So we applied KVL and we written, right? So VL equal to minus V naught. So that negative output I am showing here. So VL equal to minus V naught. And then what about the switch? How much voltage the switch is going to block? So the switch is going to block VDC plus V naught. So for this, again, you apply KVL in this particular loop. Okay, so plus VDC. So now take this as drain and this as source. Okay, so here plus, here minus. Drain as plus, source as minus. So I can apply KVL as plus VDC minus VDS minus VL equal to 0 from this. VDS, the drain to source voltage, I am getting it as VDC minus VL. So what is VL in the mode 2? Minus V naught. So if you substitute VL as minus V naught, I can get the drain to source voltage is equal to VDC plus V naught. So it is blocking the positive voltage of VDC plus V naught. Whereas if you see the diode voltage in the mode 1, you can check here VAK equal to minus of VL plus V naught. So VAK equal to minus of VL plus V naught. So what is VL here in the mode 1? VDC. So minus of VDC plus V naught. So it is blocking the reverse voltage in the mode 1. The diode is blocking the reverse voltage in the mode 1. So whereas in mode 2, the switch is blocking the forward voltage, positive voltage in the mode 2. The switch is blocking the forward voltage of VDC plus V naught. Okay. So now the switch current is 0 since it is turned off. And what about the diode voltage? So in the mode 2, the discharging current circulates through the diode. So it is in on state, the voltage across the diode is approximately 0, and whereas the current through the diode follows the inductor current, the discharging manner, the discharging direction for the inductor. Okay, the discharging current of the inductor comes to the diode. Okay, and what about the capacitor? It is in charging state and it follows the inductor current nature. Okay, so this is what the capacitor current and diode current. Okay, so these are the model waveforms for the various elements present in the converter. So this is what we have seen for the buck converter and as well as the boost converter. The same thing I am presenting for the buck boost converter. So just apply KVL and get the equations, the blocking voltages, and you can see the current, inductor current as a reference. The same inductor current is going to flow through the switch when it is turned on. When it is turned off, the same inductor current is going to flow to the diode. The discharging inductor current flows to the diode, whereas the charging inductor current flows to the switch. So this is what for the buck converter model waveforms. Okay. So we applied average voltage across inductor 0 over a 1 cycle. Similarly, you can apply average current through capacitor is 0 over a 1 cycle. So that principle, and you can come to the average inductor current. How much is the average inductor current? So as seen for the boost converter, the same thing here also. So when the switch is turned on, the capacitor is in discharging state. So it is written as IC equal to minus I naught. Whereas when the switch is turned off, the capacitor current, I can write it as IC equal to IL minus I naught, because IL is here and then I naught is here. I naught is here. I naught is here. So if I want to find the capacitor current, okay, which is here, so IC, I can simply apply the KCL here. I can write IC equal to IL minus I naught. So this is the capacitor current in the mode 2 and this is the capacitor current in the mode 1. Okay, now again you apply the principle of average current through a capacitor is 0 over a 1 cycle. So you can write this equation. So minus I naught into T on, that is D, plus IL minus I naught, which is the mode 2 capacitor current, into T off, that is 1 minus D equal to 0. So now when you simplify this, the average inductor current you are getting it as I naught by 1 minus D. I naught by 1 minus D. So again, you can verify the input current also, input current, average input current also. So that average input current is equal to switch average current. So what is the current flowing in the switch when it is turned on? Inductor current. So again, if I neglect the inductor current ripple, so I can make the IL is equal to I naught by 1 minus D. So that is the current flowing in the switch during turn on state, that is D. Okay, here it is T on. T on I can replace it as D. Plus when the switch is turned off, there is no current in the switch. Okay, so now the average switch current I can write it as I naught into D by 1 minus D. So this is the input current only. So the average switch current is equal to input current because they are connected in series. Okay, so if you can verify the input power as VDC into I switch, so average of the switch current. Okay, so average of the switch current I can write it as I naught into D by 1 minus D. So you know VDC D by 1 minus D. So that is equal to V naught. So we just now derived, right? So V naught equal to VDC or Vs into D by 1 minus D. So I can write it as V naught. So as the converter is in ideal state without any parasitics, so the input power is becoming equal to the output power. Output power. So that is what the analysis for the buck boost converter. Okay, anyways, so I want to explain what is the practical application of this buck boost converter. So where this buck boost converter is going to be helpful to you. Let me take one example. So you are having a 48 volt source. So my source is having 48 volt. Now, suppose here the load is going to be vary. Suppose in example case 1, I am having a load requirement of voltage at 24 volt. And in the second example, I am having a load requirement of 60 volt. 60 volt. So now you can observe the same converter is going to perform and it is going to be helpful for both the loads. So if I take example case 1, 48 to 24. So then the converter has to do the buck operation. So if you see the output voltage equation, V naught equal to dVs by 1 minus t. V naught equal to dVs by 1 minus t. If the duty is less than 0.5, you can verify that the output voltage is less than input voltage. So this converter, the same interfacing converter is going to perform the buck action. So again, I want to change my load. So now my load requirement is 60 volt. Now, without changing a converter interfacing system, so the same converter is going to perform boost operation, and the voltage is going to be stepped up from 48 to 60 with the application of duty greater than 0.5. Greater than 0.5. So in one case, duty can be made as less than 0.5 to meet this load requirement and operating this converter in buck operation. In another example case, the duty I can increase greater than 0.5 and I can meet the load requirement of 60 volt to perform the boosting operation. So that is the importance of buck boost converter. So where the output voltage requirement is wide range with respect to input. So there you can apply this buck boost converter. So this is what the analysis present behind the buck boost converter. So now let us see the design of L and C. So how to design the values of the L and C. So as we have seen in the boost converter, the same principle here also. So one thing you need to remember for the converter analysis, again and again I am saying, so when you want to design L, you need to look into del I, the ripple in the inductor current. So where this del I comes means with the KVL equation of voltage across inductor. So you write a KVL equation and get the voltage across inductor. So from here only you can get the del I. Del I. From this particular equation, you can design value of L. So that I'm going to show you now. So during a buck boost converter operation in mode 1, we mentioned that VDC equal to VL, VS equal to VL or VDC equal to VL. So how I can write VL? L into di by dt. That is equal to VDC. Since this equation I considered in mode 1, so the change in time I can take it as T on. I can make this as a D into T. So from this I can take del I equal to VDC into d into t by L. So where this t, if it goes to down, I can take it as F. So I can write del I as VDC d by LF. So once the design equation is formed, so based on the user requirement, suppose I require some ripple current of 1% or 10% or 5% of the average inductor current. So I can consider del I. And VDC is known for the user, and based on V naught and VDC relation duty you can able to figure out, and the switching frequency you can able to figure out. So you can design the value of L required for the converter operation to maintain the current ripple within the limits. So that is where we are doing for all the converter. Not only this converter, not only boost converter, buck converter, any converter. So if you want to design the value of L, you need to look into del I. So where this del I comes means applying a KVL in a loop, either in mode 1 or mode 2, and get the value of VL, get the equation of VL. So from this VL equation, you can get the L, design of L. So this is what the design of L equation for the buck boost converter. If you observe, the boost converter del I and the buck boost converter del I both are remaining same. So boost converter also we written del I equal to VDCD by LF. So similarly for buck boost converter also, so del I equal to VDCD by LF. So for boost converter and buck boost converter, del I equation remains same. The design of L equation remains same. So now let us see for the capacitor. So capacitor. So capacitor again for the capacitor, what I mentioned for buck converter, boost converter. So see the capacitor current waveform. So when I see the capacitor current waveform here for the buck boost converter. So it is looking similar to the boost converter waveform also. So you can check when the switch is closed, the capacitor is discharging to the load. So similarly, it is happened in the boost converter also. So that's why when the switch is closed, we return minus I naught. Minus I naught. When the switch is open, the capacitor comes to charging through the inductor and the supply. So and we understood that it follows the same shape as a inductor current nature. Okay, so this is what we have seen for the capacitor current for the boost converter. Now the same thing applicable for the buck boost converter also. So from this, I can make the change in Q, del Q, as I naught into dt. So just I'm finding the area under the curve. So here it is I naught length. What is the breadth here? T on. T on I can write it as D into T. D into T, where duty is the D is the duty cycle, T on by T. So I naught into T on, I can write it as I naught into D into T. So the change in Q equal to C into change in V, because this is well known for us. Even we have seen in at the buck operation, boost operation also the same equation. So from this I can write del V as I naught D into T by C. So again, I can take this T towards the denominator side. I can write it as I naught D by CF, where I can do I naught in terms of voltage also. So del V equal to V naught D by RCF. So this equation can be followed for the design of the capacitor. Design of the capacitor. So del V is going to be specified by the user. So V naught, you are going to note, it is known to you. Based on V naught and VDC relation, you can find the duty value. So for buck boost converter, you know the relation between V naught and VDC. V naught equal to dVDC by 1 minus D. So from this, you can able to calculate the duty value. That duty value you can substitute here. So the load resistance, it is known to you, and the switching frequency is known to you. So based on this, you can design the value of capacitor to maintain the voltage ripple within the band, within the your particular requirement. It may be a 1% of output voltage, average output voltage, or 5% of average output voltage. It completely depends upon the user. So this is about the design of L and C for the buck boost converter. So now let us see one problem for the boost converter. So the design problem for the boost converter, you can just go through this problem. So we are going to use the same equations what we derived in the previous video lectures. You can just have a look over this problem. So they given a boost converter. So for a application, they are using a boost converter, and the output voltage of the boost converter, they are saying it should be 8 volt, and the output current is 1 amp. So just I'm writing the given data here. So the output voltage is 8 volt and the output current is 1 amp. So what they're saying, input voltage varies from 2.7 to 4.2. So you can take the example of solar renewable application, where the input voltage is unregulated. It is going to vary with respect to radiation. So according to this question, the input voltage is varying from 2.7 to 4.2. So even though input voltage is varying, so they implemented some control circuit to make the output voltage constant, and the switching frequency they taken as a 200 kilohertz. So now we need to determine the value of inductor in such a manner that the ripple current should not exceed 40% of average inductor current. Similarly, the voltage ripple should not exceed 2%. 2%. So just you can see the given data here. So from the V naught and I naught, I can have the load resistance as 8 ohm here. So what is the main requirement they given? So we need to design a value of L and C in the boost converter. In the boost converter, we need to design a value of L and C so that the del I should not exceed 40% of average inductor current, and del V should not exceed more than 2% of the output voltage. So now the same thing I written. First we'll calculate the value of L, the optimal value of design, L design, optimal L design. Then we follow the optimal C design. Okay. So what is the requirement they given? 40% of IL average. Okay, fine. So here, as the input voltage is varying, one thing you can understand, as the input voltage is varying, definitely the control circuit is adjusting with the help of duty ratio to make output voltage constant. So now let me take the output voltage for the boost converter as V naught equal to V in by 1 minus T. So now let me take one example, example case 1, where the input voltage is 2.7 and the output voltage is 8. Now I calculated the duty. And the example case 2. So the control circuit is going to adjust the duty. So to make the output voltage constant with the input voltage of 4.2, again the output voltage is 8 volt only. So but here duty ratio will change D2. So now our target is, in any of these case, the current ripple should not exceed 40%. Similarly, the voltage ripple should not exceed 2%. Okay. Anyways, we are getting two values of duties, D1 and D2. In both the cases, we need to satisfy this condition. Okay. So now, if I take D1, so I'll be getting the average inductor current some value. If I take D2, I'll be getting the average inductor current some value, because we already derived the average inductor current equal to I naught by 1 minus D for boost converter. So IL average equal to I naught by 1 minus D. So you'll be getting two values of average inductor currents. Okay. So now if I calculate del I for this value of average inductor current, this is coming as 1.18, and for this value of average inductor current, it is coming as 0.761. 0.761. So again, you take these two del i's and calculate the value of L. You know del I formula VDC D by LF. So VDC you take for particular this VDC of 2.7. Similarly, in the second example, you take VDC of 4.2 and make the duty of this D2. So now when you calculate, you are getting two values of L. So one case you are getting 7.55 microhenry. In another case you are getting 13.1 microhenry. So which one you are going to select? So you select whichever is the maximum value, so that it satisfies the other condition also. Suppose if I take 13.1 microhenry, okay, L2. So if I take this L2, okay, and if I check whether the first example is satisfying or not, okay, I'm going to check now. You can verify this, whichever the larger L, that L value you can take. So and you can verify whether the first condition is satisfying or not, whether the inductor ripple is maintaining less than not more than 40%, not more than 40%, you can verify. So let me take the example of this. So del I am taking and verifying the first example case where the duty is 0.6625 and the average current is inductor current is 2.962. Okay. So del I VDC, and the VDC is 2.7, V in is 2.7. So I am substituting VDC D and then L. The second example case L, I said optimal, right? That value of L I am substituting here, and the switching frequency is 200 kilohertz. So you can check the del I is coming as 0.682, which is less than 1.184. So definitely it is not more than 40% of average inductor current. So that is why I can consider the L2, the second example case designed L2. I can consider it as optimal. I can select this value of L2 for the application, for this particular application. Similarly, you can go through for the capacitor design. So del V naught D by RCF. So again, so here the required condition is not more than 2% of output voltage. So 2% of output voltage is 8. 2% of 8 is 0.16. So now again with two duty values, you can calculate C1 and C2. Here also, whichever the value of capacitance is higher, that value of capacitance you can apply for the operation. Consider it as optimal and apply for the converter operation. So that is what you can verify here also. You can verify the second example case by substituting the C1. By substituting the C1, 8 into 0.475 divided by 8 into 20.7 micro, as I consider the C1 as the optimal value and F as 200 kilohertz. So you can check here 0.114. 0.114, it is less than 0.16, so it is satisfied. So the first the calculated C1, I considered it as optimal value, whichever the main trick is here. So whichever is the highest value of C, you take that as optimal. In the design of L also, whichever the highest value, that you take it as optimal for the operation. So that will satisfy the second, the another operation also, that operating condition also it is going to satisfy. So this is how you need to design the value of L and C for the particular converter. Again, you need to look into the voltage stress also, voltage stress across the switch and diode. Suppose if you are implementing a buck boost converter, so you need to take a switch rating which can able to manage greater than VDC plus V naught, at least 1.5 to 2 times of VDC plus V naught, so that for safer side. So you need to see the switch data sheet and select a switch which can able to block greater than VDC plus V naught. Similarly for the diode. So they select the diode which can able to block the reverse voltage of VDC plus V naught for the buck boost converter. Similarly, you can check for the buck converter also. For buck converter, I guess it is going to block input voltage, that is VDC, for both the switch and diode, whereas for boost converter, the switch and diode should block output voltage of V naught. So you need to know about these output voltages and input voltage. So based on this only, on the blocking requirement of the switch and diode, you can able to select a appropriate switch. So with this, I'm closing the session. So in this particular video lecture, we started with the introduction, what we discussed in the previous video lectures. After that, we started with the buck boost converter analysis, and then we have seen a design equation of L and C for the buck boost converter. At the end, we have seen a problem for the boost converter. The same problem you can carry out for the buck boost converter also for the design of L and C. Thank you very much. We'll meet in the next video. So if you're having any doubts again, so I request everyone to join the group. You can contact me. So we'll be discussing further.